In this video, I will explain to you how to run general linear models in R. We generally run general linear models if we have a continuous y variable, and we can have a continuous or a categorical x variable. In R, we use the function lm to run a linear model. And I just want to make the point that linear models are a broad set of models that include regression and ANOVA analyses, which you may have learned about in your stats courses before. But I will be referring to them more generally as general linear models or linear models, because we use the same function for them and because this term general linear models is all encompassing. It includes all linear models regardless of whether the predictor variable is continuous or categorical, or whether you have one predictor variable or several predictor variables. We're going to be working through the code and very systematically, and especially focus on how we interpret the model outputs. I will provide the material, the code and the data to you so that you can also run it on your own. We will be working with a data set that I have read into R already. I have called it data table, and this is what data table looks like. It has 3 columns. The first column is weight, which has numbers in it, so it's a continuous variable. The second has fat, which is also a continuous variable, also has numbers in it. And the third variable is sex, which has categorical variables in it. And in this case, we had males, indicated by M, females, indicated by F, and then a few other people for which we didn't specifically record the sex. So we cannot say whether they're male or female, so we have just called them unrecorded. We will be running 3 different models. The first model looks at the effect of fat on weight. All right. So let's have a look at the code that we have on the screen here. I am creating a new object here called weight fat model. I have decided to call it weight fat model. You call it anything you wanted to. And this symbol denotes that I am creating this new object over here. All right, and I'm saying into this object, place what is on the other side of the symbol, namely the content of a linear model, LM. And when we write a linear model, we put the y variable first, then we use a tilde, and we put the x variable. Okay, because my data is in the table data tables, I use this notation, data tables, dollar weight, and the dollar means pull out the column weight. So we want to have the column weight in the table data tables as a y variable, and we want to have the column fat in our table data table as our predictor variable or our x variable. Okay, it's very important when we think about these analyses to know whether we are dealing with a continuous or a categorical x. Even though all our code is the same, regardless of whether we are working with a continuous or categorical x, in terms of interpreting the model, it's important to know. Okay, as I said, always in linear models, our y variable is always continuous, but our x variable in a linear model can be either categorical or continuous. And now we're starting off by looking at an example where x is a continuous variable. Right, if you have a continuous x and a continuous y, you are looking for a straight line relationship. Okay, you're looking for a line, and we describe the line in terms of its intercept And we won't really be talking about the intercept in today's lecture, but very importantly, the slope of the line. How steep is that line? Is very important. And of course, a line can have a negative slope, like in this example. It can have a positive slope too, which would go the other way. And sometimes we find that there's no effect of x on y, in which case we will have data points that are not different to a straight line. So if we have a straight line, as x changes, y does not change. Alright, so I've set up my model. The code is in, on how to set up the model is in the code I've given you. I've run my model according to the code on the previous page. And the first code I then run is summary of the model. Alright, so summary and weight fat model is what I called the model. So this is what we type in ourselves. Remember, you want to type it into the RStudio panel in RStudio and then send it to R. When you send it to R, in the bottom left panel, R prints this over here. The first thing that it prints is an indication of what formula we have run. And you can see we've run a formula where weight is predicted. This is what the tilde means by fat, right? And we have here information, quite a lot of information here, and the information right at the bottom here represents statistics on the whole model, and what we have in the top here are statistics that are related to the particular predictor variable that we have put into this model. Okay, in this case we have only one predictor variable, fat, so actually our whole model stats are the same as our stats just for the single predictor variables. But if you add more than one predictor variable, so if you were to add sex here, these values would no longer be the same. Okay, so I'm going to go through each of these sections systematically so that you know how to interpret them and how to report from them. The first thing I want to point out is when you are running a model with a continuous variable, then you will see that our x variable, the way it is printed here, is identical to the way it is printed here. Data table fat and data table fat here. So please pay attention to that, because when we're running a categorical variable, this changes. And in that case, these will not be identical. You will see examples of this. So if these are identical, so just check when you're running your model and you need this variable to be continuous, make sure it looks exactly the same here as it does there, and you know it is continuous. Again, you can see both weight and fat are continuous variables here. Okay, how do we interpret the model? Let's first look at the whole model results. We have a few different variables we can look at. The first is the R squared. All right, this is the amount of variance explained, and it's a proportion out of 1. So an R squared of 0.69 means that 6.9% of the variation in weight is explained by our model. That's not a very good R squared value. If you're doing sort of field work, an R squared above 0.3 or 0.35 is probably acceptable. If you're doing experimental work, we would usually want it to be a bit higher, maybe around 0.5 or 0.6, to indicate that we have strong results. It also depends a bit on the number of samples you have, but in this case, our amount of variation explained is small. It's only 7%. The other important variable that we have here is our p-value. Remember that every p-value tests the probability of the null hypothesis being true. Right? Again, this can be converted to a percentage. In this case, it would be a percentage of 17.6. Right? So there is 17.6% chance that our null hypothesis is true, and the null hypothesis here is that the model explains no variation in weight. Okay, 17% is a fairly small amount, but usually we use 5% as the cutoff. So as long, or 0.05, a probability of 0.05. So as long as this value is larger than 0.05, we cannot reject the null hypothesis. So in that case, we have to say that this model explains no variation in weight because our p-value is not smaller than 0.05. So we cannot reject this null hypothesis. If our p-value here was smaller than 0.05 or 5%, then we could say that the model does explain variation in weight, and we could reject our null hypothesis and accept our alternative hypothesis. So these are two very important whole model variables. The other important variable you can see here that we need to report are our F statistics and then the 2 degrees of freedoms. So you don't need to interpret those in the text, and I'm also not going to explain to you what they mean here. But when you are writing up your results, you would say our model explained no variation in weight. Then you would say R squared equals 0.07, p-value equals 0.18, and F statistic F equals 1.932, and DF, degrees of freedom, equals 1 and 26. Right, so you would report those results in a bracket. So what can we see here? Right, so let's move to the bit of the coefficients table, which tells us something about each of the predictor variables. Again, we have a p-value. In this case, the p-value here is the p-value for fat. So we always have a p-value for each of our predictor variables. And because fat is a continuous variable, in this case, our null hypothesis is that fat has no effect on weight. All right. So as fat increases, weight does not change significantly. Right. So this is a graph with a slope of 0. That's our null hypothesis. We can see that again our p-value is 0.176. So we cannot reject our null hypothesis. So in this case, we must say that fat has no effect on weight. There's no significant difference because our probability that the null hypothesis is true is just too high. We are very conservative. We want that p-value to be smaller than 0.05, and in this case, it's bigger. The other important variable here is the estimate. The estimate is if we are working with a continuous variable, it represents the slope, all right? So the slope here is not exactly 0, even though there's no significant effect of fat on weight. We still have a slope that is a positive slope. So that means if you were to draw a line through your figure, that line would have a positive slope, so there'd be a direct relationship between fat and weight, but that relationship is not significant. So in this case, if we were to interpret our results, we would say that fat has no effect on weight. Even though we have a positive slope here, that slope is not significant. So our interpretation is that fat has no effect on weight. We can also plot our result, of course. And here we look at the effect of fat on weight. And if we plot our points, in this case, we don't put a line through it because this relationship between fat and weight is not significant. Our p-value here is bigger than 0.05, so we couldn't reject our null hypothesis. Right, let's go on to our next example. In our next example, we have a categorical X variable. All right, here we are creating a new model. We've called this model weight sex model. And in this case, we are looking at the effect of sex on weight. Okay, because we have categorical variables now, our figures would look different. So on the X axis, we can have different values. So in this particular case, remember we have 3 different possible values for sex. The one is M, one is F, and the third one is unknown. All right, if we had another, if we added another one, we could have more boxes. All right, but in this case, we've got 3 different levels for our X variable, which is sex. And in this case, we are not looking for a trend, but we are looking for differences in the means of these different X variables. So we would look for a difference between, say, female, male, and unknown, whether the weight of those is different. Okay, so we need to word our analyses a little bit differently too. Okay, so we would run exactly the same model, the same LM code if we have a categorical X as we would as if we had a continuous X. So the structure of the LM code would be the same. And this is what our printout looks like. It looks very similar. Again, here we have the code we ran. So this is what we typed into RStudio ourselves and then sent to R. This is the formula that gets printed. So all the bit that's in black is printed by R. This is the formula that's run. So you can see we're using sex, trying to see if that affects weight. And we again have statistics related to the predictor variables. In this case, our predictor variable is sex. And then we have whole model statistics. Okay, now very importantly, if you have categorical predictor variables, you will see that these names now change. Okay, remember we had male, female, and unrecorded values in sex, and we can see in our code we said please look at the effect of sex on weight, but in the printout it doesn't just print sex, it prints sex M and sex unrecorded. Right, and M in this case refers to males, that is the level here, and unrecorded, the level there. Basically what it shows us the levels, all the levels except the first one in the alphabet. In this case we have F, M, and unrecorded. So it only shows us M and unrecorded because F is the first one in the alphabet and it is set to 0. Okay, so I'll explain a little bit more about that. How that works, but it's very important to check that this value here looks different to these values when you are dealing with categorical variables. Okay, so let's first again go to the whole model statistics, what we have here at the bottom, and recap it. It's basically the same principle as for the previous model. So we have the R squared. In this case, the R squared is much better. It's sitting at 0.23. So we can say 23% of the variation in weight is affected by sex, or is explained by this model, which has only sex in it. We have the model P. Remember here, the null hypothesis is that the whole model explains no variation in weight. But our p-value here is small. It's smaller than 0.04, so we can reject our null hypothesis, and we can say that this model does explain variation in weight. And then remember that we also need to record these values. Okay, the next thing we now need to do, before we look at the coefficients table on the summary output, if we have a categorical X variable, is we need to run this code, ANOVA weight 6 model. Okay. The reason we need to run this code is because we want one p-value for the variable sex. So we want to know what is the probability that sex affects weight. All right. Here our p-value is 0.04. It's a small value. Again, it's the same as the whole model P because we have only one predictor variable in the model. But here we can reject our null hypothesis that sex has no effect on weight because our p-value is smaller than 0.05. So we can say, therefore, sex does affect weight. Okay, so the reason we need to run this ANOVA when we have a categorical X is because, remember, in the coefficients table, and I will show you again just now, it didn't only give us one line for sex, it gave us a line for sex for each of our levels of sex. So it gave us one line for male and one line for unknown or unassigned. But we want one p-value for sex. We want to know does sex have an effect or not. So in this case, our interpretation is that sex does have a significant effect on weight. Okay, so we now know that sex has a significant effect, but we actually want to know which of the sexes has the highest weight, which has the lowest weight, and we also want to know, are females different to males, are females different to unknown, and are males different to females. So we need to run all of those models. So we will do that, or run all of those comparisons, or assess all of those comparisons, and that's what we'll be looking at in the next slide. Okay, so we go back to the summary table, which we were at before, and we look now at the coefficients table, right? And some of the answers are here. Again, we have p-values, so it looks very similar to the coefficients table where we had continuous predictive variable. But remember, we have more than one line for sex here. And what this line represents is the difference between the sex indicated here, so that is M for male, to the sex that we cannot see, which is the first one in the alphabet, which is female, right? So the p-value that is tested here is tests the null hypothesis that males do not have a different mean weight to females. Okay, you can see the p-value here is smaller than 0.05, so we can say males do have a different mean weight to females. In the second instance here, we are testing the null hypothesis that unrecorded individuals do not have a different mean weight to females, and in this case our p-value is larger than 0.05, so we cannot reject the null hypothesis. So here we can say males have a different weight than females, a significantly different weight than females, but unrecorded individuals do not have a significantly different weight to females. Okay, so we can tell that. What we cannot tell here is whether we have a significant difference between male and unrecorded, and we will look at that just now. The other thing that we cannot tell only from the p-values is whether the males tend to have a higher weight or a lower weight than the females, and the same for unrecorded. And for that, we look at the estimates here. So these estimates show the value of the mean for males with regard to females. And remember, I said females are set to 0. So in this case, females are set to 0 when males are 16.289. So that means that the mean weight of males is 16.289 kilograms more than that of females, and the mean weight of unrecorded is 12 kilograms more than females. We can also calculate the difference between males and unrecorded, and that would be 4.289. So we can say males on average have a weight of 4.289 higher than unrecorded. So we just subtract these two from one another, but we still need to ascertain whether these two values are actually significantly different to one another or not. So we need to know what is the p-value here significantly different to one another. Okay, so let's just recap. What does this coefficients table tell us? So we know from the previous slide that sex has a significant effect on weight. And if we want to decompose that statement, we can say males have a higher weight than females, and the weight of unrecorded individuals is not different to those of females. But we do not know whether the weight of males and unrecorded individuals are significantly different to one another. We do know that males is higher than unrecorded because this mean is higher than that mean, but we do not know whether they're significantly different. So for that reason, if you have a categorical X variable, you need to run one more line of code, and that is this EM mean, where you put the name of the model in it, and then you say, you provide the variable, the name of the categorical variable which you want to compare. So you need to type pairwise the tilde and then provide whatever your categorical variable is. In this case it was sex. Okay, and we will concentrate on this table at the bottom, and this table gives us all three comparisons. The previous table only gave us female male and female unrecorded, and these are the same p-values that you will see on the summary table for female male and female unrecorded, but it also gives us the p-value for the difference between male and unrecorded. And we can see we have a p-value of 0.794, which means that the difference between males and unrecorded is not significantly different. Okay, so again we have these p-values. They test for differences in the mean. So each p-value tests the hypothesis that the mean between these two here are not significantly different. So in the first example, it tests whether females have, or it tests the null hypothesis that females do not have a different mean weight than males. Here our p-value is smaller than 0.05, so we would reject the null hypothesis and we would say females do have a different mean weight. And here we look at the estimate, and we can say, because females are mentioned first here, this shows the difference between males and females, and it shows us females are minus 16.29 smaller than males. All right, that's the same as we saw in the previous table. We have a p-value for the testing the null hypothesis that females and unrecorded have no different weight, and we also have a null hypothesis that unrecorded do not have a different mean weight to males. All right, and in both these cases, our p-values are larger than 0.05, and therefore we do not reject these null hypotheses. And so we can say females have a significant smaller weight than males, and then females and males do not have a significantly different weight to unrecorded. Okay, so we could see these two from the previous slide already, but we did need to test for the third hypothesis also. Okay, and then we can draw a very simple plot in R or in Excel, and you can see the mean for female here is about 16. It was around 16 lower than males. It was 12 lower than unrecorded. And we found that females were significantly different to males. So if we want to put this, indicate this on a graph, we can use letters, right? Females is different to males, so they should have different letters. But females was not different to unrecorded, so they should have the same letter. And males was not different to unrecorded, so this should also have the same letter. So this is one way in which you can present your results on categorical variables. Okay, the last model that we're going to be looking at is if you have more than one X variable. And the example I'm giving here is where we have one categorical and one continuous variable, but you can also have two continuous or two categorical or two categorical and one continuous. So there's all different types of combinations. And really these models work on the same principles as the two types of models we've spoken about now, but I'm just illustrating how we interpret these just so that you can also run the models and fully understand them if you have more than one predicted variable. So I've created a new model called combo model, and in this case I look at the effect of both sex and fat on weight, because we would expect that it's not only sex and it's not only fat that affect the weight of a person, but a combination of these two And so if we think that more than one variable affects our y variable, we add both of them to the model. All right, once again, what does our output look like? Okay, so here I've typed again, I've indicated what the model is, and I've typed the summary of the combo model. Again, this is the code we run. And again, in the R output, it shows us the model that we've run. So weight is affected by sex and fat. So basically reproduces what we've typed there. And again, it gives us the whole model stats and the stats related to the predictor variables. Again, very importantly, let's compare what we have at the top here to how it's presented in the table. So, and for fat, the text is identical, and so that indicates to us that R reads fat as a continuous variable, which it should. In contrast, you can see that the way sex is written in the formula looks different to the way it is written in the coefficients table. All right, again, we see, we don't see sex F, so the female, because it's the first one in the alphabet, so it's excluded, but we see M and unrecorded behind here. So we know that it's written, that it is read by R as a categorical variable. Okay, so how do we go about this? Again, we start off by reporting the whole model statistics, and we've done that twice now, so I'm not going to repeat it, but all these important variables that I mentioned before in this section need to be reported. So we know how to do that. The next thing is we want to test whether sex and fat have an effect on weight. And so again, we can run the ANOVA function, so ANOVA and then the name of the model. And here we get two p-values. The one p-value is for sex and the other p-value is for fat. And remember, each p-value has a probability associated with it. In this case, the first probability is that sex has no effect on weight. The null hypothesis is that sex has no effect on weight. And for the second probability, the null hypothesis is that fat has no effect on weight. Okay, and we see that both of these have p-values smaller than 0.05. So this E minus 0.5 means E minus 0.5 means times 10 to the power of minus 5. So it's 1.265 times 10 to the minus 5. So these are very low p-values. So we can reject both of these null hypotheses. So we can say sex has an effect on weight and fat has an effect on weight. All right, again, we want to have details. How does sex affect weight and how does fat affect weight? So for that, we go back to our summary and we start off with looking at fat. And remember, fat is a continuous variable, so we are looking to see what the slope of fat is like. So this p-value, in this case, tests whether fat has an effect on weight. Our null hypothesis says fat has no effect on weight. But our p-value is very small, so we reject the null hypothesis, and so we can say fat has an effect on weight. And again, because this is a continuous variable, this p-value is the same as the p-value in the ANOVA output. So you can get this p-value either from here or from the ANOVA output. But for a categorical variable, you need to get it. You don't have one p-value for sex here, so that's why you need that ANOVA table to get one p-value for sex. All right. We know that fat has an effect. Now we want to know what is the nature of the effect. Does weight increase or does it decrease as fat increases? And we can see that we have a positive slope. The slope is larger than 0, and therefore we can say there's a direct relationship between weight and fat. So as fat increases, so weight increases. Then we also want to look at the effect of sex. Okay, so sex again is a categorical variable, so we interpret the information in the coefficients table slightly differently. Our p-values in this case are whether the weight of male tests whether the weight of male is significantly different to the weight of females. For the first one here, so the weight of males, we compare it to the weight of females, which is the first one in the alphabet, which we cannot see. And this here compares the weight of unrecorded to the weight of females. What we cannot see in the table is the comparison between males and unrecorded. Okay, but we can see that we can reject this null hypothesis that the weight of males is not significantly different to the weight of females. So we can say the weight of males is significantly different because we have a very small p-value. It's 2.91 times 10 to the minus 6. And we can also reject this null hypothesis that the weight of unrecorded is not significantly different to the weight of females. So we can say the weight of unrecorded is significantly different to the weight of females. All right. And we want to also look at the estimates to see how the weights differ. So we can see that the weights of male is higher than the weights of females, and we can see that the weights of unrecorded is significantly higher than the mean weight of females. We can also see that the weight of males is significantly higher than the weights of unrecorded, but we can't see whether this difference is significant. And that's why we need to run that EM means now. But let's quickly go to the interpretation of the coefficients table, so only of this table here. We can see that females have a significantly smaller weight than males here. From the slide line, we can see that females have a significantly smaller males than unrecorded from this line. And we can see that fat has a significant effect on weight, and that effect is as fat increases, so does weight. All right, so don't only say there's a significant effect, you need to describe the pattern. So you need to say, for example, as fat increases, so does weight. Or you can't just say sex has an effect, you need to say sex has an effect, and the effect is females have a significantly smaller weight than males, females have a significantly smaller weight than unrecorded, and we still want to test the difference between males and unrecorded. All right, so that's what we cannot tell from this. All right, we now run this EM means code to assess the pairwise differences between all the levels in our categorical variable sex. And we again see these comparisons between female and male and female and unrecorded. And we see that the p-value here represents the null hypothesis that there's no difference in the weights of males and females. The second p-value here represents the null hypothesis that there's no difference in the weights of females and unrecorded. And both of these are already presented in the summary table. We can see that both these p-values are smaller than 0.05. So as we already said previously, we can reject the null hypothesis and we can say there is a significant difference between females and males, and there's a significant difference between females and unrecorded. But we are particularly interested in this comparison between males and unrecorded, which is not shown in the summary table. And here our null hypothesis is that there's no significant difference in the weights of males and unrecorded. Again, our p-value is smaller than 0.05, and so we can say that we can reject the null hypothesis and that the weights of males and unrecorded is significantly different, right? We don't only want to say there are significant differences, we want to describe those differences, and for that we go back to the estimate. If the estimate is positive here, it means that males have a larger weight than unrecorded. So in this case, the way we interpret the estimate is that the first level mentioned here is the one that is the reference. So if we have a positive number, that first level is higher than the second level. So in this case, male is higher than unrecorded. If the estimate is negative, it means that the first level is smaller than the second level. So in this case, female is smaller than unrecorded by 19.2 kilograms. All right, and here males are bigger than unrecorded by 12.8 kilograms. All right, so in summary, we can say that females have a significantly smaller weight than males. You can tell that from this, but we knew that from the summary output already. We also knew from the summary output that females have a significantly smaller weight than unrecorded, but we see that males have a significantly larger weight from unrecorded, and that is the new thing that we could tell from this summary output. I just also shortly want to address something that some of you may have noticed. We ran one model where we only had sex, we ran one model where we only had fat as a predictive variable, and then we had one model where we had both fat and sex as predictive variables. We had exactly the same data that we inputted, but our results changed based on whether we had both variables in the model or only one variable in the model. So for example, if we looked at the effect of fat on weight, if we only had fat in the model, fat was not significant. But once we added sex to the model, fat became significant. So in this latter model that we've run, if you go back to the previous slides, you will see that fat became significant. Similarly, or not similarly, but in the same way, when we only looked at the effect of sex on weight, we found no significant difference between the weight of females in unrecorded and the weight of males in unrecorded. But once we added fat to the model too, these two differences became significant. Why does this happen? So the reason that happens is that the model interprets the output differently if you have more than one predictive variable. In this example, the combo model, so the model with both predictive variables, assesses the effect of sex on weight after the effects of fat have already been considered, and it considers it measures the effect of sex on weight after the effects of fat have already been considered. All right, so if we only looked, for example, if we only looked at the effects of fat on weight, we didn't have a significant effect of fat on weight. But if we controlled for sex and we said, look at the relationship for males and look at the relationship for females, or consider that females and males are not the same, that relationship became significant. Okay, so that's why you need to think very carefully in your own models what predictive variables you need to include in the models. So some of you will have only one predictive variable, but others will have more than one predictive variable. Okay, so in summary, all the models that I have shown you, we looked at 3 models and all of them are linear models. We used the code LM for all of them, and the code was very similar for all 3 of them. So the R code is available for you, so please have a look at the R code if you are running linear models. Once we've run the models, we need to interpret the outputs, and that's why we use the summary function, and we use the ANOVA function, and and in some cases we will use the EM means function. What we need to get from our outputs is the whole model statistics. So that was in the information at the bottom of the summary table. We need to know the significance of each of our predictive variables. So in this case, we needed to know the significance of sex and of weight. If that predictive variable you have put in is significant, you also need to know, if it's a continuous predictive variable, what the slope is. Is it a positive slope or is it a negative slope? So as x increases, does y increase or decrease? And if it's a categorical predictive variable and it's significant, then you need to know where those differences in the levels lie. So is male different to female? Is female different to unknown? Is male different to unknown? Okay, so these analyses, these reports on the slope or the EM means reports are only required if your variable is actually significant. So for example, if we had found in our model that sex had not been a significant predictor of weight, then we would not have needed to run those EM means codes. But we did find that sex was a significant predictor, so we wanted to describe how sex affects weight. In the same way, in the first model, fat was not a significant predictor, so we can't say anything further. We can't say as fat increases, so weight increases, or so weight decreases, because we say there is no significant effect. But in the second model, we found that fat was a significant predictive variable. So then we were interested in the slope, and we wanted to know, is that slope positive or negative, and we found it was a significantly positive slope. I hope this has clarified linear models for you somewhat.